Well, welcome to Chapter 3, the first part, Sections 3.1 through 3.4, an introduction to recursion. And I don't know how much you've done at looking at recursion in other programs, but basically, recursion is where a program can call itself some multiple numbers of times until it gets a value and then it works its way back up through it. And so the first four sections here talk about recursion, a little bit of the theory behind it, talks about using it for factorials. But then we will get into, in the following week, we'll get into the famous Towers of Hanoi recursion program that I remember working with as a student. And certainly, given the way the languages are now, Java and otherwise, it's a whole lot easier to move those rings from those pegs now than it used to be. But we'll get into that. And then at the very end of the chapter, we'll talk about fractals. And my first introduction really to fractals was by a former head of the math department, Dr. Paul Sisson, and some of y'all maybe had his wife for an online physics class. She was a professor of physics. So we had Paul and Cindy Sisson, and for a while he was even dean of computer science. Chair of computer science when we didn't have a head. So he spent part of the day over in the math department and part of the day over with us. But Paul really got into creating some interesting math with fractals using recursion and all, even with uh, much smaller type programs than you're seeing in Java and all that. But before we get into the lecture, I just wanted to say what a wonderful job y'all did on the homework. Uh, I think everybody had full credit. I think one person still owes me maybe one more of them. And some of y'all, for what you did on the sort and drawing it out, had extra credit. As say, the homework assignment there in chapter 1 was worth 25 points, and several of you had 30 points for how you drew out the sort and all of that. So this week I'll be posting some assignments on the exercises on chapter 2. And as always, I want y'all to continue to, even though I'm not assigning programs directly, since you have the link for these programs, I want you to be running some of them just on your own, just to see how they work, maybe modifying them a little bit, uh, just where you get some practice with uh, working with Java on these various uh, data structures. Of course, we talked about probably a test here after chapter 2. And so I'm going to be coming up with some questions. I imagine your test is going to have a short answer part, similar to what you did on the exercises there in chapter 1 essay. I'll get some of the exercises here on chapter 2 out to you later in the week. But I imagine the test is probably going to have a couple of parts to it. One part where you'll answer some questions, short answer type discussion. And then another part is where I'm going to want you to run several of the programs here in chapter 1 and chapter 2, especially on creating the various ways, arrays, linked lists, traversing through, things like that. So part of it will be short answer discussion, part of it will be programs, and on the programs you'll just print out the output and attach that to those. So I'll be sending you some more info on that as we get through this week. And of course, we had the Centaur Parade yesterday. We've got coming up this weekend, you've got Gemini, you've got Highland parades, all of those things. So, just kind of be aware if you go to a parade, be careful. Of course, the school is closed on Monday the 28th and Tuesday, March 1st for Mardi Gras. I'll still be around if you got any questions, of course, but that's kind of where I'm thinking for right now. But these first four sections here, chapter 3, really just talk a little bit about recursion, give some examples. Um, as I say, recursion is where something is defined in terms of smaller versions of itself. So they go through and talk about the factorial. Well, of course, the factorial, remember, is the sum of all of the values of n, where n goes from 1 to whatever. So if you add factorial of 4, then remember that value of 4 factorial would be 4 times 3 times 2 times 1, and that would be equal to 24. So if you look at the standard definition, it says if n is 0, then n factorial is 1. Otherwise, if n's greater than 0, then n factorial equals parentheses n times n minus 1 in parentheses times n minus 2 in parentheses times n minus 3, so on and so forth until n is equal to 1. So you have all the permutations of n number of elements. So just, think about that as we get into it. So then we have the recursion algorithm on it, definition, and so we get on into a little bit of code there on top of 166, where they say if n's not equal 0, if n equals 0, excuse me, the double equal sign in the book reminds me of how we used to define things back in PL1 with a not symbol type of deal. So you have that there, top of 166. And of course, that code is out there on the chapter 2 apps, chapter 3 apps, I should say. And so it just creates it. So if n is equal to 0, it returns a 1, else return n times factorial of n minus 1. So remember, right up here at the very top where they declared this program factorial, then you notice it said public static int factorial, which it takes as an argument the integer value n. So you provide n and it takes it there. And of course, here we're talking about direct recursion. So it would, if we gave it an n of 4, then it would say, okay, is n equal to 4 logic? Is 4 equal to 0? No. Well, then it returns a 1. Else, it returns n time factorial of n minus 1. Well, that factorial n minus 1 there in the parentheses is the recursive call, direct recursion. So it says, okay, we'll call recursion. Okay, so it calls factorial n. Okay, so it does it for 3. Is 3 logically equal to 0? No. Okay, come on down. It returns n times factorial of n. Remember, it's made n then a 3, so it's in factorial of 3 times 2. So then it goes on around once more. It cuts it down to 1. It says, okay, is n 0? No. So comes on down, factorial of 1 is 1, of course, so then it starts unwinding. So it goes back up. It says, is n equal to 0? Yes, it is. So then it says, okay, well then a 1. So then it just works its way backwards, each one building on 1 factorial, which is 1, 2 factorial is 2, 3 factorial is 6, and then 6 times 4. So then it gets on up there to 24 as it works its way through it. So you have those values where it does each of them. So 4 factorial is 4 times 3 times 2 times 1. And each one of those, it just returns the preceding value and works its way backwards. So real simple in this case, dealing with factorials. As I say, it also mentions the idea of direct versus indirect recursion. Remember, direct is where it calls itself. Indirect recursion is where that A calls B, B calls A type of deal. It can keep hopping between the two until finally A returns a value and then it unwinds itself. but I have never had to use indirect recursion, only regular recursion a few times. So just be aware that those are out there. So it talks about, and that's very, very good up on the top of 167, about whether recursion or doing an iterative loop is more efficient. And as I say, it's a matter, and as you get more experience with programming, then you'll certainly become more cognizant of the differences between able to make choices. I say that a lot of that is, as we'll get a little bit into 3.8, but as you get into the second half of the course, 346, and you really start looking at the efficiencies of programming. And not only will you look at efficient ways, whether it's a loop, whether it's a do while, a do until, whether it's an if statement, whether it's recursive, all of those things. But as you grow in your programming experiences, as you are developing larger programs, certainly what language initially you use and what features within a language, all of those lead to what's going to be the most efficient for you to program in. So they talk here, well, if we used a while statement instead of recursion, then we could have, an integer of return value of 1. And we're here on the top of 167. Of course, this code is out there in the text sample programs. So it says while n is not equal to 0, remember the exclamation mark meaning not, then return value equals return value times n, and then n equals n minus 1. And then once it finishes that loop, then it returns the value of the return value. So it's got two variables, return value and n. Normally, you're going to have fewer variables in a recursive method process rather than iterative. But also, though, a loop, just a simple while loop, like in this case, takes up much less memory and machine cycles than starting or calling a method for a recursive statement. So as I say, you look at both of them. They're both there in the chapter 03 apps, the code for them. Pull them down and look and see and run them on your machine. See which one is more efficient for you on your computer and how it handles it. So that's really the section 3.2. 3.1, and you get here into 3.2. And as I say, this is really getting you a little bit into systems analysis, programming life cycles, software development life cycles, things like that. And other things it's looking at here in these three questions is, can we prove that an algorithm is correct mathematically? And there's been certainly a lot of discussion in the literature and otherwise, even back when, I was on your side of the desk there on the initial degree in 1983 of, can we prove mathematically that a program works in all cases? And so those are very, very important to remember and to look at. So just be aware that you have these three questions. The base question is, and all three of these have to be answered correctly with yes, is there a non-recursive way out of the algorithm? And does the algorithm work for the base case? What happens on the previous one if n equals 0? Logically, then you return a value of 1. Well, that's the base case. Okay, we've solved what happens if we get to the various things, because we're going to work our way down from 4 to 3 to 2 to 1 to 0 in that case. Then the second question is the smaller caller question. does each recursive call to the algorithm invoke a smaller case of the original problem? We do it for 4. We do it for 3. We do it for 2. We do it for 1. Okay, then we go to 0. That drops back to the base case. And so we wind our way out of it. As I say, it says they're leading inescapably to the base case. Well, for a positive value, therefore our n works. And then it says, question 3, the general case question, assuming that the recursive calls to the smaller cases work correctly, does the algorithm work correctly for the general case? And yes, it does. But, you have to think about, okay, well, how does this recursive program work, or doesn't? What are some input constraints? Well, think about factorial. In our case, it has to be a positive number, 0 and above. If we gave it a negative number, well, we would wind up with an infinite loop, because if we gave it a -4, well, we get to the code there and it says n -1. Well, if we gave it 4, it'd be -5. So we'd keep growing and growing and growing, and the program would never stop as such until we either A, ran out of memory, B, ran out of time, type of deal, or somebody did a physical reset of the computer or whatever. So, before you even look at doing any type of recursion on a factorial, of course, you probably need to make sure, as a if statement or otherwise, that you make sure you have a positive number. So, as I say, with each time through, it's got to produce a value closer to the base case. And so, talks a little bit about writing recursive methods, as say, coming up with an exact definition, and we've talked about that in the past couple of lectures. And that's one of the hardest things with any algorithm, is what is the exact definition of what we want to do. And so we talked about the universal method. We've talked about things there. As so you have an exact definition. You determine the size of the problem, identify a base case, and then you solve the general cases correctly in terms of smaller cases. But as I say, you got to make sure that it will work. You don't want an infinite loop in debugging. You'd run out of stack space. And a lot of times you want to use branching if statements rather than while statements. And even as we'll look at here in a couple of minutes, here in section 3.3 and 3.4, very much the order that you put your statements in. And we'll look at with an if and a print and an adjustment statement type of deal on whether it's going to work or not. So as you're getting into recursion, and I say, thank goodness that Java has some things built in for calls and passing of values, a lot better than a lot of the earlier language do. Let's say the LL node in dealing with linked lists there in 3.4 is certainly a wonderful thing to have. And so just kind of be aware that you've got to go through, make sure very carefully your order of operations, your order your statements, things like that for writing your code. So allow for all 3 of those cases where you get down to the base case, return your value. And as I say, recursion is another tool. Just as you learned initially about if statements, case statements, do whiles, do untils, all you're doing really is learning different tools to help solve a problem. And the further you get in programming, computer science, and otherwise, the more of these tools that you'll be able to rely on. As I say, you'll ultimately, by knowing several languages, be able to first choose the language or package to solve what you want. And then you get into specific code. So that's a little bit here out of 3.2. So you get into 3.3 and they start talking about recursive processing of arrays. And they talk about a binary search. And I don't know how much experience you have with binary searches, but of course, you look at what we did in previous search, sorts type of deal we've looked at, and we'll get a little bit more of this later on. But a binary search is where you're trying to find a given element of a sorted list or array. And as I say, you already know that it is in proper order, normally ascending. But a binary search is actually pretty efficient because if you know the index of your middle point and you know what you're looking for, an element. So with each time you search that array, you look, okay, is it in this group? Okay. So we look at an element. So they talk in this case of assuming an array is sorted, and we pass a target element of 20. And we know that if our elements are sorted in proper order, then if we're looking for 20, and as you see in our array, the first position is a 4, or the 0 position, I should say, because remember, Java starts their indices at 0, one of the few languages that does it. So our value sub 0 is 4, our value sub 1 is 6, our value sub 2 is 7, our value sub 3 is 15, our value sub 4 is 20, and our value sub 5 is 22, and our value sub 6 is 25, and sub 7 is 27. So we have 8 elements in this array. So the first thing it does is it says, okay, well, we're going to add our first index to our last and divide by 2 to give us a midpoint. So then, okay, so it takes 0 plus 7. So you get 7 divided by 2 is 3.5. You round up as such. So then it looks at the fourth position. And so then it looks in the fourth position and it says, oh, well, our values sub 4 is equal to 20. So since 20 is greater to 20, what we're looking for, then we know that it appeared in the fourth position. And so it's all the time calling each of these different values. If it's equal, look at the value at midpoint. If it's returned true, if it's less than, then it sets first to the midpoint plus 1. You take the top half. Or if it's less, you set the less to the midpoint minus 1 type of deal. And so you just keep working your way through it, looking at the individual elements until you find what you're looking for. Well, what if we were looking for 18? Or we get to 8. What if, the middle element was 18 instead of 20? Well, remember, it goes through, and each time it's either adding 1 to first or subtracting 1 from from the end of it, the last. So it says, okay, first greater than last, and it returns false. So in that case, if we were looking for 20, but we found 18, well, notice it would say first would be an element eventually 22, so number 5, and last would be equal to location 4, which was 18. So then we wouldn't find it if we were looking for a 20. So it's kind of a little weird on this binary search where you're going through and you're saying, okay, the base case, if first is greater than last, then returns false. So that's how we get out of it ultimately, is saying, hey, well, we can't find it, so it's false. Otherwise, if it's less than the target, return the target and midpoint plus 1. And last, if the value of midpoint is greater than, then returns target first and midpoint minus one. So it's just going half and half each time, making it smaller and smaller slices to look at. So it talks here about on 173 saying, okay, if first is greater than last, then the returns false. Okay, so there are no elements to search. If the value submidpoint equals the target, then the algorithm returns true. It says, okay, hey, the midpoint element, we found it, and that's what we're looking for. So, but then you look there for the smaller question, smaller caller, I should say, the general case and the binary search is called with parameters. So as I say, if it returns the general if midpoint is less than the target, then the search is the target. It adds one to the midpoint and last, so you get a new first. Or if value submidpoint is greater than the target, then it returns the midpoint. Then it returns the search of the target first midpoint minus one. So it gives you as such a new last. So you just as you're working through, it will do those things. So you have like top of 174, as I say, that is called Boolean binary search. It's the name of the file out in cho3.apps. So we have integer. Okay. So we have integer declared, midpoint is first plus last divided by 2. And so then it says if the index of first is greater than last and returns false. Otherwise, I say looks at the value of if the target number is logically equal to the value of midpoint, then it returns true. Else, if it's smaller, the target's past it, then it divides it in half and takes the left half. If, on the other hand, if the target is too low, then it keeps where we're at and subtracts one from the midpoint until it gets there. So let's say binary searches are kind of are a good one to use. Let's say you could do it recursively. You could do it with iterative. And it just kind of depends on what's easier to say. You're going to get into some very unique areas of working with the efficiencies, and we'll get to those later on. So the last section here they talk about is recursive processing of linked lists. And in this case, they're only going to do where that we're going to add a node to the end of a linked list, or we're going to print out a linked list, either in forward ascending or in descending. So you have a list of links, the elements and their links. The last element has null for its link. And it talks a little bit about self-referral classes are closely related to recursion, or they are recursive. But in dealing with linked lists, as I say, we're only doing a little simple part here. Later on, either in our class or 346, you will get into how to do other types of additions, deletions, all of those things with linked list. But as I say, a linked list can either be empty or it can have nodes which contain information and a pointer to the next node in the list. And sometimes I'm going to call it a node, or sometimes I'm going to say, the address of a pointer. And that's just the way that I got used to talking about there, the link from one element to another one. I say whether it's a link, a pointer, it's all the same thing, really. So, if you're traversing a linked list, they show like on the bottom of 175, well, we're just going to print things out. So it has a little bit of code where you just keep processing and printing until you get to a null value for the pointer. So you see the code there up on the top of 176 is listRef not equal null. So listRef, remember, is the pointer. It says otherwise print line listRef sub get info. So it gets that value in this first case of A. And then you see rec print listRef get link. Well, what does that do? Well, that then sets up the next value as it gets the get link, goes into listRef, and then listRef returns back into it. So it just keeps looping until. And so it passes the base case type of deal. And then it says, okay, there's a way out of it. When we get to a pointer of null, then we stop. Okay, so the general smaller case is it passes the list reference by the listRef get link, which is one node smaller. Remember, just keeps working its way down through there until it finds a null reference, and then the general statement. Rec print listRef will get link correctly prints out the first element followed by the rest of the elements like that. So I say that's just a simple way of traversing a linked list. I say you can do it iteratively, you can do it recursively. In this case, it's basically about the same number of steps, a little more processing, probably internal, with a recursive question than with a iterative, but you notice essentially very much the same things there. So you have also, you could have a little bit of code there, 177, top just showing, hey, we could go through and work our way through how many elements. We're just going to count the number of elements type of deal. So it just returns the size. Then you get to the bottom of 177 and type of deal. And top of 178, but saying, okay, well, what if instead of printing A, B, C, D, E, what if we wanted to print E, D, C, B, A, printed in reverse order? So notice here, if you wanted to do it, notice it's just really the difference in the order. If n is not null, you get the next location and print the element there in 178. But if you go back on 176 and you notice there, it prints, then gets the next. So that's really the difference between the two. The code is as such there, they both stop when they get a value of null. And so, but notice you're getting here on the one there on 176 where it prints it out in order. It prints it there where you print, whereas in the 178, you get the next location and then you print the element. And so, you've got to look at, as I say, so much in these. You'll get a clean compile, all of that. But if you have your steps out of order, then of course your logic will be backwards or whatever. So they also talk here about, well, what if we want to add things on 178, 179? What if we want to add cat after our linked list of ant and bat? And so they get here a little bit into it. Well, if list sub get link is null, then it adds it to it. Else, it sets the link to the next link. So you have a little bit here, and it goes into a little bit of the logic of and saying, hold on, well, yeah, you have that, but if we get into it, then there might be a problem. And so this works fine as you're traversing along with a standard linked list And if the link is not equal to null, then it gets the next element. Well, that's great. It gets the next one, it keeps going until you finally get to where you have a null, like there on the top of 181 of bat. So then it says, okay, well, then if we have bat and the link out of bat is null, then we put cat and then we set the reference for bat going to cat, and then nothing happens with ant because there's no change there. But there's a problem, as the book points out, on you have an empty list. If you don't have anything in there, then how are you going to handle it if you have nothing? So they've added a little bit of code there on there saying, what if we have a empty list? What if it's equal to null? So you're saying, okay, if you check for if it's not equal, not if code checks for not equal, empty, or null. So if it's true, then it sets list ref subset link, and it calls itself again rec insert end sub new info get link. False, it sets the list ref to new sub ll node string. So there you see a little bit there in the middle of 180 where it says list ref equals ll node string. They just set up where if the first one it hits is a null, then it says, okay, we have an empty list. So then I have to put cat, and it's represented by pointing to our linked list points to cat with a null pointer afterwards to itself. So just kind of be aware. I say it talks about until my list points to ant, which points to bat, to a null reference. So then it invokes, and it says, okay, it inserts cat, and the link of bat now points to cat. Cat's link is null, and then it works its way back out. And as I say, no change to ant. But you've got some code here. They do it for several values. But the main thing to go through is just stressing not so much the coding, but how it handles if they're blanks, if it's empty, or otherwise, of how do we handle the linked list. So do some thinking there. As I say, I'm going to post this part out there, but there'll also be some things later in the week on some homework type of deals. So be aware of that. And as I say, y'all keep doing what you're doing. Let's say I really enjoyed what y'all found out on the ACM website. Several of y'all, said, hey, I'd never thought of this area. This looks like a new area of computer science that I hadn't thought about. And as I say, you get a student membership. I had one when I was on your side of the desk. Haven't done much professionally. But as I say, I know that some of y'all are very much into graphics. And there's a whole special interest group called SIGGRAPH. And I see a lot of stuff otherwise with it. So, as I say, keep doing what you're doing, and I'll get you an assignment on Chapter 2 out in the next day or so, and some more information later in the week on test 1 here on chapters 1 and 2. And as I say, probably going to have you just run some of the programs that are predefined here in the chapters, as well as some short answer discussion type questions to think about. And that's what I know. So keep me posted and call or email with questions. Have a great week.